In this video, I'm going to talk about how we can use relationships between graphs and kinematics graphs and kind of estimate things. So in the previous video, we talked about how you can use slopes and areas to calculate other values from a given graph. Here I'm going to talk about how we can actually estimate what the other graph should look like from looking at one to start. So this is going to require me being a little bit cleaner with my sketches. So it will take a little bit more time. So we're going to start with a position versus time graph. So this is again position versus time, x versus t. And let's just imagine something that looks like this. So now, if I go to my velocity versus time graph, if we remember, the way that we can find velocity from a position versus time graph is look at the slope. So I notice here at the beginning, for this first 2 seconds, my slope is 0. So I'm going to start it here. I also notice at the top here, for maybe these last 3-ish seconds, my slope is also 0. So I know kind of these points like this. And let's say here. So the slopes are basically 0 from there. Then I see that my slope increases for a while, and it hits its maximum right about here. That's where the steepest slope is. And I'm just going to really roughly estimate it as 3 by looking at going up by 3 and over. So right in this region here, I need to get up to 3. So 1, 2, 3. I need to basically be right around 3 for this whole region here. Again, that's because we have the steepest slope. Then I see that it goes up kind of at a constant rate because it gets steeper and steeper at about the same rates. That should be a more or less straight line. And then over this whole region, it slows down at about a constant kind of curve. It's a nice smooth curve. So then I should expect kind of a nice line coming back down to a stop here. So that's how we estimate these ideas. We basically draw our lines based on where you see those slopes. So then, same thing for acceleration versus time, except now I've got nice straight lines, so I don't have to estimate as much. I know here there's no change in the velocity, so my acceleration has to be 0. In this region right here, it's also flat, so my acceleration has to be 0. Because again, the slope is 0. And then down here, the acceleration has to be 0. And then we can just look, this has a slope of positive 3 over 3 seconds. So that has I'm just going to label a 1 here. It has an acceleration of positive 1 over that whole region because the slope is constant. And then here, that's a slope of negative 3 over 1, 2, 3, 4, 5, 6, 7, 8, let's call it 9. So that would be 3, negative 1/3. So again, I'm going to be a little sloppy in my diagrams here, but we'll call that negative 1/3. And that's how we do it. We just look at those slopes and kind of carry them through. If we have a velocity versus time graph, let's start in the middle and work our way outwards. So I'm going to start like this with a velocity versus time, and I got to be a little careful with this. So let's go say sorry, I'm just planning some things out here. And then we'll go say 2, and then we will go back down to here, over, and up. Okay. So this will be position versus time, and this will be acceleration versus time. So now if you recall, the way we get to position, acceleration versus time we'll do because it's like the last one. So this first region, I rise by 4 over 2 distance. So we're going to call this my 1, this my 2, this my -1, this my -2. So I start off with acceleration of 2 for 2 seconds, because again that's the slope. Then I have 0 slope for 2 seconds. Then I have -2 for 2 seconds. And that continues, we're a little sloppy here, but we'll just pretend this continues for another second. Even though that might look a little more like 3, slope of -3 to you. Then we have our 0 acceleration for a while, because again it's a flat, there's no change in velocity. And then I have +1 for a while, for this last 3 seconds, just like that. So that's my acceleration versus time sketch from my velocity curve. Now, if you remember, we said that the velocity versus time is the slope on my position versus time graph. So once I get from here to here, I need to have a slope of 2. So let's draw that as something like that. And then for the first part, I'm speeding up until I get to that. So my slope needs to increase until I get to that. And this always happens with this sketch. Then I slow down back to a stop over 2 seconds. So slow down back to a stop over 2 seconds. And again, we know we're stopped because we have this horizontal line. Then I start going in the negative direction and speeding up. So I'm going to speed up, go to a steeper negative slope. And then this whole time I've got a constant negative velocity. So I have a constant slope that comes down. And eventually I level back off and come to a stop. Now, how did I know I have to go into the negative region? Because if I look at this and eyeball it, there's more negative area than here. And we can calculate that as well to figure out exactly how far. So in other words, over this whole region, maybe up to this point, you know, I was counteracting, I was coming back to where I started, but now I'm keeping moving in the negative direction, so I keep having this negative area here. This is another thing that as you go, you'll get more comfortable with this. It's something you kind of need to practice, get feedback on, practice again. So don't stress if you're not 100% on it. Lastly, let's look at acceleration versus time, and this is going to be using that idea that we just did about velocity, or sketching the position versus time from velocity, but we're 2 layers deep now. So acceleration versus time, we'll start with something like this. And it's flat for a while, and then it's up here. So I'm going to sketch, I'm not going to worry about getting the numbers exactly right, because I want to be cognizant of the time here. So starting off, we have it get more negative over time. So my velocity needs to go downwards. I need to have a negative slope, negative constant slope. I can start wherever I want. I can say I was already moving, or I can say I was starting from rest, or I can say I was already moving the opposite direction. We don't know from an acceleration versus time graph. So I'll just pick starting from here arbitrarily. Now we see that it's got a slope of -3, so it's a real steep downward slope. Then we have no acceleration, so I come across at a constant speed. Then I have a slightly less acceleration for a while, so I have a slope that kind of comes up like this. Now if we look, there's more area under this than there is under this. This has 9 boxes. No, sorry, there's less area. There's 9 boxes here, there's 8 boxes here. So even though I go for a slightly longer time, I don't actually get back up to the same velocity I started with, because this doesn't give me enough basically positive acceleration to counteract the negative acceleration from earlier. And again, some of this isn't super critical long term. It's just, or sorry, some of it's not critical right now. It's just me planting seeds that will hopefully come back later. So lastly, position versus time. we look at this again, and I see, oh, I've got negative x. I start out moving in the positive direction, and then I turn around here and start moving in the negative direction. So I'm going to see something like this. And then I move in the negative direction for a while, negative, constant speed. And then here I come to a stop and start moving back up in the positive direction. So because I was at 0 here, that's my rest point. Those don't quite line up, but those should. And then because this is all positive velocity, I should have my object moving up on my graph. So lastly, let's look at doing some calculations from a graph. So this is a problem here. A stationary car is stopped at a traffic light. When the light turns green at t equals 0, a truck with constant speed passes the car. The car uniformly accelerates to its top speed in 15 seconds and then moves at a constant speed. The truck is represented by the dotted line and the blue car is represented by the solid line. How long will it take for the car to catch up with the truck? So what we first want to do when we're solving this, kind of using this reasoning, is we want to figure out how far ahead or how far they've moved at given points and basically look to see when they're the same. So let's just go up to 15 seconds and see where we're at. So after 15 seconds, the one that's moving constant, so the truck, has moved 30 meters per second times 15 seconds, which is 450 meters. The car has moved 40 meters per second times 15 seconds divided by 2, because we're calculating the area of this blue triangle. So 40 times 15 should give us 400 plus 200, that's 600 meters divided by 2, which is 300 meters. So they haven't matched up yet. And now if I look, this area right here, I'm going to do a little shortcut in the reasoning. You could guess and check. Just guess every 5 seconds, see if they travel the same distance. But what I notice here is every 5 seconds, there's a difference here in area of 50 meters per second of 10 meters per second times 5 seconds. So this area represents a change in position of 50 meters. In other words, the car goes 50 meters further in this time than the truck does. And if I look at this, these difference is 450 meters. So if the car travels an extra 150 meters, they'll make up the difference between them. So that will be after 3 units of time, so at 30 seconds. If you want to double check this, you can just calculate the area under this curve, which is going to be an extra 15 times 40. Which we said, if you remember earlier, was 600. So this is 900 meters for the car. And for the truck, it's just an extra 15 times 30. Sorry, 15 seconds times 30 meters per second. And this should be in meters per second. And that equals 900 meters. So they're both at the same position. They both have traveled the same amount of distance. They've matched. So again, any type of geometric reasoning you want to use is fine as long as you're doing it carefully. Let me know if you have any questions, but otherwise we'll wrap up here.